Poi si avvia sempre anche la trascrizione che non ci interessa, però adesso la sta registrando.
Ok.
Ok.
Okay, good morning to everybody. Welcome to this third class about the behavior of curved and twisted beams. Today, this morning, I will speak, and in the afternoon, instead, Fernando Fraternali, Professor Fraternali, who is here on my left side, will continue the topic. So in the first two classes, we have seen the basic machinery of curved beams, especially at the beginning, the fundamentals of differential geometry as ideas about the beam. Then we have seen what we do mean by beam, so a particular solid which behaves in such a way that its curved axis line can deform freely, but the cross-section, who is at the beginning perpendicular to the, in each position to the axis line, is forced to remain plane. So the formation of this solid is somehow restricted, and so we can think of having some internal constraint which make the formation of the beam a particular kind of deformation. Then, by using the principle of virtual work, we have been able to devise governing equations, which come in different flavors, because we have some field equations which must hold for any point of the arc length. And then we have some boundary conditions which depends instead only on the two left and right end of the beam. So in particular, we have seen yesterday that in the most general case, so that of a space curved and twisted beam, we have these equations which you see on the back here. Sorry. So we have equilibrium equations which connect what we can see as the resultant and resultant moment at the section level projected on the three moving axes, so in the respectively binormal, one direction, principal normal, second direction, and tangent, third direction. The first three equations are relevant to the linear momentum balance, so balance of forces. The last three equations, again, projected in the direction of the binormal, of the principal normal, and of the tangent, are relevant instead to the moment, and so these can be interpreted as angular momentum balance. Then we have, someone wants to come, okay. Then we have, here it's written constitutive equations, but indeed this is a mixture of two things. We have some compatibility conditions, which are again given by the principle of virtual work, and connect the generalized strain to the generalized displacement of the beam axis and the rotation of the cross section. And again, we have, so these are the left hand side of these equations. And then we have combined them with constitutive equations, which are instead not given by the principle of virtual work, but come out as a different, let's say, statement that we can make based on different hypotheses. Here, what we see is the extension of the classical de Saint-Venant theory to the case of curved beam. And we have seen that this formulation can hold only when the curvature and the torsion of the beam axis are relatively small, in the sense that the ratio between the radius of curvature and the radius of twist compared to a characteristic length of the cross-section is large. Then we have, of course, the boundary conditions which connect which take into account the effect of constraint of the beam. So, as it is usual for beam problems, we can either prescribe at one end of the beam the force, or we have to prescribe the value of the corresponding displacement. When I talk about corresponding, I mean that they are conjugated through the principle of virtual work. So here, for instance, at the left end, where S equal to 0, we either prescribe the shear force, or we have to prescribe the displacement in the direction of the shear force. For the one direction, for the two direction, for the axial direction, so we have the axial force, which must balance a prescribed force in the exact direction, or we do not know what is the value of the axial forces there, but then we have to prescribe the value of the corresponding displacement. The same happens for moments, as we see here. Of course, these are the boundary conditions relevant to S equals 0, and these are the corresponding boundary. And this make a distinction between a natural boundary condition, which come out from the, let's say, extension of the principle of virtual work, or forced boundary condition, which must be are kinematic conditions that we have to enforce when we write down the kinematic problem. So yesterday with Professor Fraternali, we have seen how it is possible to use constitutive law which are more suitable for strongly curved beams or strongly twisted beam. And now we want to analyze in detail the easier case of planar beam. We can say that... what?
You can mute him.
Who is the...
This is one mind. Okay, Gianni. Gianni. Okay. I don't know if it was Gianni or someone else.
Anyway, okay, we have muted him. Sorry for, but if there is any request for explanations, you try to raise your hand or something similar. Otherwise, we must go on. So, as I was saying before, we say that the beam is plane if its axis is completely contained into a plane. Let's say it's pi, capital Pi, and to have a planar problems, we need that all forces acting on the beam and the displacement produced by such forces must be contained in the same plane. A typical case is that when a beam has a plane of symmetry where all forces are acting in the same plane. So in this case, if we consider as a plane perpendicular to the direction of the binormal, so vector B, unit vector B, then we can denote by R the direction of the principal normal, and by T the direction of the tangent at any point of the axis line. So the situation is depicted in this picture. here, where we say that we can devise the tangent direction t and the normal direction r, or radial direction, which are at any point of the axis perpendicular to each other. Instead, so we can associate to this direction the displacement component Vt in the tangent direction and Vr in the radial or normal direction. And of course, we can further see that the axial force M is directed along the tangent direction. The shear force T is instead directed along the normal or radial direction. The bending moment M is instead perpendicular as a vector, is perpendicular to the plane of the beam, so its vector has the same direction as the binormal. And to this moment is associated as a kinematic variable the rotation of the cross-section, which is denoted here by phi. So in the previous formulation, it is, if you want to adopt this new convention, substitute index 1 to B, index 2 to R, and index 3 to T, since R and T belong to the plane of the beam. And then if we substitute in these equations we have seen, sorry, before, in these equations we substitute index 1 with B, index 2 with N, index 3 with T, we get a simpler set of equations which is more familiar to our to standard notation, let's say. So in particular, we see that what is the generalized component of the pseudo vector sigma? The third component is indeed the axial force. The second component is indeed the shear force. And the fourth component is indeed the bending moment acting on the normal plane. The corresponding strains are instead epsilon, which is the axial strain, gamma, which is the shear strain associated to the direction of the normal, and theta, which is the section, the angular strain associated to the bending moment. The corresponding generalized displacement are, of course, Vt, which is the displacement along the tangent curve, Vr, which is the displacement acting along the normal direction, and the rotation, cross-section rotation phi, which is aligned with the binormal direction. So the compatibility equations can be written in this way by selecting the proper terms from the previous formulation, which is this one. So if you look at the left-hand side here, and we select only the equations which are relevant to the second component, which is the normal direction, to the third component, which is the tangent direction, and to the fourth element, which is relevant to the angular moment, to the compatibility condition in terms of the angular distortion, we see that we get exactly these equations. Here, there is a little change in the sense that we are also taking into account the presence, which is denoted here by epsilon star, gamma star, and theta star, of distortions. So prescribed strain acting along the respectively the tangent, the normal, and the angular directions. Instead, on the left-hand side, epsilon, gamma, and theta must be thought of as the not the total generalized strain, but the generalized strain associated to the stresses by the constitutive law. So, if we do the same things for the equilibrium equations, we get a set of 3 equilibrium equations. The first 2 equations are those relevant to the behavior in terms of linear momentum balance. The third is a component of the only non-vanishing component of the angular momentum balance. And so these are the equilibrium equations, and these are the compatibility conditions. As we see, both these equations are coupled in the sense that the tangent behavior in terms of epsilon involves both tangent and radial component of displacement, as well as the shear strain is linked to both the radial and tangent displacement and also to the rotation phi. The same happens to the equilibrium equation in the sense that if the beam has a curved axis line, then the displacement equations in the equilibrium equation in terms of the tangent direction is also influenced by the presence of shear force, as well as the equilibrium equations in terms of projected along the normal directions gets a contribution for the case of a curved beam by the axial force. Here instead, for what is related to external forces, we see that there are tangential distributed loads, radial distributed loads, and the distributed couples. So, of course, as we will see later in details, if in particular the beam happens to have a straight axis line, then curvature becomes zero, so radius of curvature becomes infinite, and so this coupling disappears. And so for the case of a straight beam axis, the equilibrium equations can be rewritten in this way if we accept to design by z the direction of the axis, which is now straight, so S is replaced by z. The opposite direction R is now denoted by Y, be the direction perpendicular to that plane, and so the direction along which the moment vector acts. So in this case, we see that if the beam axis is straight, these coupling terms from the first and second equation disappear, and we get simply the usual equilibrium equation of rectilinear beams we are accustomed to in standard strength of materials classes. Okay. In particular, if we look at the last equation of equilibrium here, in the absence of distributed couples, we get the fundamental relations between the derivative of the bending moment and shear that tells us that, of course, shear force is exactly the derivative with reference to the axis line of the bending moment. Now, let's put things together, and so we can try to write down the constitutive equations expressing the link between the generalized strains, so epsilon the axial strain, gamma the shear strain, and theta the angular strain, and the applied generalized forces, axial force N, shear force T, and bending moment M. In this case, we have written down the equation for the case of extension of Descent-Venant behavior. And we see that in this case, exactly, epsilon is related to N over EA. E is a Young modulus and A is the area of the cross-section. Gamma is related to the shear force T multiplied by this He, which is a shear correction factor, which according to Descent-Venant theory takes into account from an energetic point of view of the equivalence of the work done by the shear force by the corresponding shear strain when we account for warping. And in the denominator we have again the area of the cross-section and instead the shear modulus G. And finally, the last equation connects the generalized angular strain, theta, to the bending moment M through the bending stiffness, which is the product of Young's modulus and the second moment of area of the beam. Here we see that prescribed strain, epsilon star, gamma star, and theta star, which can take the place of strain, for instance, due to thermal effects or something like that, are something that influences the general constitute a compatibility condition, but the relation is between epsilon and N, gamma and T, and theta and M. In particular, we can have some extra simplifications in the sense that we can assume that our beam is unable to experience, let's say, shear strain. So a beam which cannot experience shear strain is a kind of beam like following the Euler-Bernoulli model. And so if we have that gamma is equal to 0, then that means that this expression, of course, T cannot be determined by the constitutive law, but only by equilibrium. And in this case, we see that there is a clear connection between the section rotation phi and the radial and the tangential displacement VR and VT. And that is the expression we get. So we could think of taking the derivative of this expression, and so we get, by taking the derivative, this expression. This derivative of phi with respect to the arc length can then be thrown into the third equation, and so allows us to get compatibility, constitutive law in terms of moment, but without the explicit introduction of the section rotation phi, because in this case, according to the Euler-Bernoulli beam, the rotation of the cross-section is linked to the transversal and axial displacement, and so it's completely determined by them. Of course, we see that taking the derivatives gets these four terms. The last one is linked to the prescribed shear distortion, which can exist anyway. And in particular, we can see that the next to the last term, this one, which since we have to take the derivative of Vt over R, so since both depends on S, we should take first the derivative of Vt at R fixed, and then take the derivative of R at Vt fixed, and so we get this expression. Of course, this expression, the derivative of the curvature with reference to the arc length, will vanish if the curvature is constant, or can be disregarded if this term is of the same order as Vt. And so often that term will not be taken into consideration in a rigorous way if the axis line is an arc of a circumference, or if it is sufficiently, the radius of curvature is sufficiently large as this term can be disregarded. A further simplification can be made if we assume that the axis line is inextensible, which implies, of course, that the axial strain epsilon must be zero. And in this case, of course, if the axial strain is assumed to be zero, we get that the derivative of this t with respect to the arc length minus the prescribed axial strain must be equal to the radial displacement divided by the radius of curvature. So if we consider the effect of all these assumptions, we can arrive at these equations, and we see that if we assume that there is both inextensibility and the beam cannot be submitted to shear deformation, the first two constitutive equations are zero, in the sense that epsilon and gamma cannot be determined by the corresponding forces, and instead the only governing equations in terms of constitutive law is that which connects the generalized strain in terms of bending moment and bending moment. So these are the globally, the boundary value problem is governed by these equations, so equilibrium equations we have seen before, the constitutive equations, which in the general case are these, and of course the boundary conditions, which involve either axial force at the end of the beam or the tangential displacement at the end of the beam, the shear force at the end of the beam or the radial displacement, and the bending moment at both ends of the beam, and the section rotation at the end of the beam. We should check now what happens if we introduce the simplification we saw before. So for instance, if we consider an inextensible Euler-Bernoulli beam, then we have to write down that gamma is equal 0 and epsilon is equal 0. So the compatibility conditions now connect only the transversal, radial, and rotation to the applied distortion along the axial direction and the transversal direction, and instead the equation relevant to the bending moment can now be expressed only through the radial and transversal displacement. It's a second order differential equation connecting these two things. We must check that in this case, of course, we have to introduce not only in the governing equation the angular distortion, but also the derivative of the transversal distortion. In this particular case, of course, since rotation of the cross-section is eliminated, we have to change the boundary condition in the sense that the first two sets of boundary conditions are the same, those connecting the axial force and the shear force to the external force applied at the end section, and or the corresponding forced boundary condition in terms of tangential and radial displacement, and instead the contribution of bending moment in terms of natural boundary condition requires an equilibrium at the end forces and moments, let's say, on the end cross sections. Instead, here we do not prescribe anything about the rotation, but rotation of the end cross section is related through this equation to the radial and the tangential displacement, and so this amount must be prescribed at both ends. Now, further simplification is to consider a straight beam. So, if you consider the first simplification, means to consider a shear deformable and extensible beam, but with a rectilinear axis lines. So we can see that in the general case, which is this one, we have to cancel the terms which depend on curvature. So in the equilibrium equation, we will cancel this term and this term. The third equilibrium equation is the same. For the instead the compatibility condition, what we see on the left-hand side here, of course, the term which connect coupling term will disappear here also, so these terms cancel out as well as this one, and so we reach these compatibility conditions and correspondingly the constitutive equation. So epsilon is only linked to the derivative of the axial displacement with respect to the arc length, which is now coordinate z, plus, of course, the prescribed axial distortion, and this is linked to the axial force. Gamma, which is a shear strain, is only due to the derivative of the transverse displacement with respect to z, plus the rotation of the cross-section phi. And finally, the angular strain, theta, is the derivative of the cross-section rotation phi, plus, of course, the angular distortion. And these are, instead, all of these quantities are determined by the corresponding values of the axial force, shear, and bending moment. And these are, of course, equilibrium equations. As we have seen before, all coupling terms are now eliminated because the beam is straight. And for the boundary conditions at both ends, we get the usual ones. So as we have seen, we have that the fundamental properties for straight beam is that the kinematic problems which involves a axial variable is completely decoupled by that relevant to the transverse displacement and the sectional rotation. And similarly, also the static problem that involves axial force is completely independent on that which connects shear and bending moment. For simplification, we can introduce is to ban the shear deformation. So telling that shear strain gamma that determined by the constitutive equation must be zero. So as we have seen before, if here we say that gamma is zero, that means that the derivative of v with respect to z plus phi must plus gamma must be zero, and so it is possible to eliminate from the formulation the value of the cross-section rotation phi. And then introducing it into the last constitutive equation, we can connect the transverse displacement v to the bending moment through this equation. And of course, in this case, boundary conditions in terms of natural boundary conditions are exactly the same as before. But if we look at the forced boundary conditions, we cannot prescribe anything about the cross-section rotation, but we can say something about the rotation of dv over dz represents the rotation of the axis line. And so the boundary condition is now given in terms of the derivative of z with respect to z. This equation if we disregard for a minute the presence of angular distortion and shear type distortion, is what we call the linearized elastica. So the elastic curve. If we take now twice the derivative of this equation, we get the linearized elastica in terms of the fourth order derivatives of the transverse displacement v, and gives us, if we take into account the equilibrium equation, which is this one, in absence of distributed couples, so that we can write down this equilibrium equation, substituting the transverse distributed load Qy, and so we get the linearized elastica as a fourth order equation. And this involves the force derivative of the transverse displacement, connecting it to the applied distributed load. And so if we integrate this fourth order differential equation, we will get a general integral depending on four constants, which must be determined by correspondingly four boundary conditions, two for each of the beam ends. And this boundary condition will depend either on V, means a forced boundary condition, or on the bending moment, which is related to the second derivative of V with respect of Z on one side. And on the other side, the second boundary condition will involve either the rotation of the axis lines, so the derivative of Z with respect to the axial coordinate z, or the shear force, which is somehow related to the third derivative of the transversal displacement. Okay. For strongly curved planar beams, the problem will be seen with Professor Fraternali in the afternoon, so I'm skipping it for now. Instead, what I would like to see is to go to the static problem of elastic arches, plane arches. And so in particular, we can consider the case of a curved beam whose axis is an arc of a circumference which is contained into the YZ plane. Such a beam would be subjected to loads Q and distributed couples C and distributed distortion gamma and epsilon, respectively along the radial this direction the tangential one, and angular distortion theta star. All these quantities are distributed per unit length along the axis line, and here it is shown the axis of the arc, which is an arc of a circumference, and so the arc length S is of course measured along the arc. We have the tangential and the normal direction T and N. B is of course the direction of the B normal is getting out of this plane. And so we can see here the positive direction of the tangential and the radial displacement and of the rotation, cross-section rotation phi. And here we have signed the positive direction of the distributed load Q and the distributed couple C. Effectively, the radius of curvature is constant, and is equal to the radius of the circumference, and the position along the axis line can be completely determined by the anomaly, so the angle measured from one of the ends of the beam. In particular, we can see that since we are working with a plane problem, the distributed load Q, which is a vector function, can be expressed by components as a radial distribution of QR and the tangential distribution of QT, which are then multiplied by the unit normal and the unit tangent vector, which, however, change from point to point along the axis line, where, of course, n coincides with the unit vector E2 and t coincides with the unit vector E3 of the moving triad. Instead, distributed couples can act only on the binormal direction, and so are projected along this direction only. So for elastic problem can be simplified when we work with the polar coordinates rho and psi, which we see here. Rho is again the radial direction, and phi is the anomaly. In particular, we see that the curvature 1 over r 1 over rho is exactly 1 over r and is constant. And so we can replace in all the equations the radius of curvature rho with the radius of the circumference r. With this simplification, we can formulate the governing equation for this particular problem by observing that since the arc of arc length S can be usually represented by the product of the radius r by the angle theta, psi, sorry, we can write down that the derivative of everything with respect to the arc length can be simply written as r d psi. And so if we multiply all the terms by the same r, we get this simplified form of the equilibrium equation. So the derivative of n with respect to the anomaly psi minus t plus qt, the tangential distributed load multiplied by r must be equal to 0. The second equilibrium equation involving t and n is now the derivative of t with respect to psi plus n plus the radial distributed load multiplied by r must be equal to 0. And the equation, angular momentum balance equation, tells us that the derivative of n with respect to the anomaly psi minus the shear force multiplied by r plus the distributed couplings multiplied by the same r must be 0. For the compatibility condition, again, we can write down this form, taking into account again that ds, the differential of the arc length, is simply r multiplied by the differential anomaly d psi, and we get this 6. Now, for arches, is often assumed shear that they are cannot be shear deformable, and that they are inextensible. In such case, the constitutive equation tells us that gamma must be equal to 0 and epsilon must be equal to 0. Instead, theta is related to the bending moment, applied bending moment divided by the flexural stiffness. For the boundary conditions, of course, at the first end, we have to prescribe equilibrium of the generalized stresses, or conditions about kinematic conditions about the value of the radial, transversal displacement and the rotation. Of course, these are prescribed, they generally are 0, but we can assign any value, meaning that in this case there are some prescribed constraint settlements, inelastic settlements at the boundary if these are different from 0. And at the generic end corresponding to psi to point B, where psi index B is a value of the correction, then the boundary conditions are of this kind. So when writing the constitutive equation as remark, we have assumed both shear undeformability and inextensibility. The cross-section is symmetrical with reference to the principal normal axis, and when writing the kinematic boundary conditions, eventually inelastic settlements of the constraints need to be taken into account. Then, combining the compatibility condition with the constitutive equation, we have these compatibility equations which connect the expressions here with the hypothesis, assumed the hypothesis that gamma is equal to 0 and epsilon is equal to 0. Now we see that if we want to solve a problem for an arch, we have to solve simultaneously a system of 6 differential equations. So differential equations in terms of equilibrium, which connect the generalized forces to the applied loads, and then this set of equations which are the compatibility conditions which are connected by the constitutive law to the applied generalized forces, internal forces. So a system of 6 differential equations and 6 unknown must be solved. So in general, it is better to develop a system to solve the problem by eliminating some of the variables in order to get a more complex differential equation, but whose solution allows us to complete the solution of the all interested and involved variables. And so we will see now how to develop the governing equation for circular arches in terms of only kinematic quantities. Maybe now could be a nice time to make a break. So after the break in 15 minutes, we will continue with this problem.
Okay.
Okay. So probably